Okie dokie. Good morning. Let's go ahead and figure out the products of this reaction. And then let's go ahead and figure out what its net ionic equation is going to be. So first, I guess we'll predict the products, and then good morning, Brittany. We'll predict the products, and then we will balance it and do our states of matter and all that fun stuff, and then we can do our net ionic equation. Welcome, say hi, dude. Let's see. Let's see if I can do this without breaking it. You gonna say hi to everyone? Or do you just want to stand there? There you go. Yes, hi little dude. Okay. There's your dog for the day. What type of reaction is this going to be, by the way? That one is Kaladin. He is my youngest one. Yes, this is definitely a single replacement reaction. So just one thing to remember with this one, we do have a transition metal present that does have variable charge. And so remember, we always want to assume it's going to be +2 for a variable charge metal. So of course copper is a metal, right? So it should be replacing the metal. Okay, sounds good, Brittany. So what are our products going to be? I'll give you one of them. Woohoo! Wow, and Sherry not only did the predicting, but also the states of matter and the balancing. Very, very nice. Yes, so you're correct, Sherry, with all of that. Very, very nice. Awesome. So, let's go ahead and now do our complete ionic equation. So remember, that's going to be to break apart aqueous things. So everything else in a net ionic equation, solid, liquid, gas, don't touch. Aqueous stuff will break apart. And remember that coefficients do carry over to all of the components of that compound. So that's why this one will have 2 silver ions and 2 nitrate ions. And as always, I run out of room and have to squish everything down. Alrighty here, so let's go ahead and look at what is exactly the same on both sides. By the way, there may be times where your net ionic everything is a spectator ion. Not in this case. This one will have a net ionic equation. If your net ionic equation is nothing, that means overall no chemistry has happened. So you might see that in certain double displacement reactions. But our single replacement ones will always have a net ionic. Okay, so looking at that, we have copper solid here. On the right side, we have copper 2 plus aqueous, not the same thing. Here we have 2Ag plus aqueous. Here we have 2Ag solid, again, not the same thing. Next one, we have 2NO3 minus aqueous. On the right, we have 2NO3 minus aqueous. Those are the same. So our nitrates will be spectators. And so we can see that our net ionic equation is going to be the parts that are still here. Oops. So with those in mind now, we can see exactly what chemistry is happening here. If we look at it, what is happening with this reaction? So we have copper that's going from solid, regular elemental copper into copper 2 plus, and we have silver ions that are becoming silver metal. We can see perhaps that what is actually happening in this is that electrons from copper are going into the silver ions. Hello, Maya. We can see that. How do we know that? We have copper going from uncharged to a charge of 2 plus. We are going to see that. Yes, Sherry, absolutely. So yes, that is exactly what is happening. Yeah. And so this means, of course, that it is losing electrons. So copper is going from neutral copper into copper 2 plus. So it's losing electrons, right? Because it's becoming more positive. If we look at silver overall in the course of this reaction, we can see it's going from +1 to 0. Let me just make that arrow a little nicer. And so we can see that this is going to be gaining of electrons. We can see that pretty clearly here in our net ionic equation. Maybe a little bit more tough to look at the plain old equation and do it that way, but net ionic equation will give us, kind of exactly the bare bones of our reaction, making it a little bit easier to see what's happening here. Alrighty, and so, yes, indeed, this is a special type of reaction we can see electrons are being transferred from one substance to another substance. And we have a fancy name for those. We call these redox reactions. And that word comes from two other words, which are reduction and oxidation. And in fact, I'm going to go ahead and just swap those two real quick, because I'm going to show you a way to remember them. We're going to see that for vocabulary-wise, oxidation is losing electrons. Oxidation is the process of something losing electrons. And we're going to see that reduction is the process of gaining electrons. And if we take the first letter of all of these, we get a mnemonic oil rig, which will help us to remember what oxidation is, what reduction is. So oxidation is losing electrons, that's oil, and reduction is gaining electrons, that's a rig. So that's how we're going to remember these. And we can see here that the word redox is kind of a portmanteau, a combination of the words of reduction and oxidation. So that's one way you can remember which one is which. There are other ones. Some people say Leoger, and I mean, there's a bunch of different mnemonics that you can look up on the internet if you like. But this one is the one I like the most. So, but anyway, it doesn't really matter what you like, or what you want to use, rather. Okay, cool. So one thing to note. These two always happen together. Meaning you can't just have one of them. So you can't just have an oxidation. There has to be a reduction that is happening as well. Because the electrons have to go somewhere. So you can't just all of a sudden lose electrons. I mean, I guess you can if you're like blasting stuff at X-rays, but that's not a chemical reaction necessarily. So in a chemical reaction, if you're going to have oxidation, you will also have reduction. They're always going to occur together. So we're going to be learning now a number of ways to predict, or rather just be able to identify what's being oxidized, what's being reduced in a reaction. So if we go up to this previous reaction, Sherry has already done the work for us, but let's go ahead and look back up at it. We see that the copper is losing electrons. If we look at our mnemonic, which one of these is losing electrons? Oh, that's oxidation. So this process here, oxidation, is going to be what's happening to our copper. And we're going to see that our silver is being reduced because it is gaining electrons. So notice again, we do have both processes happening. One of them, the copper, is being oxidized. The other one, the silver, is being reduced. Let's go ahead and bring back one of our equations from yesterday. I don't know why I wrote the whole thing when I want us to look at the net ionic equation. We can do that. Okay, so now let's go ahead and figure out what's happening here in terms of oxidation and reduction. So again, looking at the net ionic equation of a single replacement reaction, we're able to see very clearly what's happening with these electron transfers. So let's go ahead and look at the two elements that we're looking at here. We have chlorine and bromine. What charge does chlorine have on the left? Yeah, it's neutral, right, exactly. So it starts at 0, neutral being 0. And if we look on the right side of the reaction, our chlorines are now -1. They have become chloride ions. Plus question mark. Kenji, explain. Okay, sounds good. And if we look at our bromine, we are starting at -1 and we're going to end up at 0. So neutral stuff is 0, right? No charge. Alrighty, so looking at this now, we can see one of these is gaining electrons and the other one is losing electrons. Which one is the chlorine going to be doing? Is that gaining electrons or losing electrons? If it's going from 0 to -1. Mm-hmm. Yep. So it is definitely gaining electrons, becoming more negative, right? So that means it's getting electrons. And so the opposite one must be losing electrons, right? And I mean, we can always double check. Yeah, of course, it's going from negative to something more positive. So it's going to be losing its electrons. And so if we go back to our vocabulary lesson, we see that oil is losing, oxidation is losing, reduction is gaining. So chlorine, who is gaining, that is reduction. Bromine, who is losing, that's going to be oxidation. So we might say, in words, chlorine is reduced, bromine is oxidized. And that is what is happening in this reaction. We're going to see that pretty much all of the interesting reactions that allow for life to happen and all the stuff that we take advantage of in our everyday lives, they're all going to be redox reactions. So like glycolysis, photosynthesis, you've got your electron transport chain. You have all those, reducing equivalents that you talk about in, citric acid cycle and all that fun stuff. These are all oxidation and reduction reactions. And we're going to see that, batteries operate the same way. Combustion reactions are all oxidation reduction as well. So, moving your car or turning on your heater or whatever, these are all redox reactions. So, fun stuff. Cool. So, for sometimes, like in these single replacements, it's easy to see what's gaining and what's reducing electrons. However, let me just write this out. with ionic compounds, it's easier to see how electrons are moving. Yep, exactly. So yeah, that's exactly right, Kenji. So all that stuff is happening. All those, NADH, FADH2s, those are just carrying electrons, for other things to use later. So yeah, it's definitely a big component. Okay, so with ionic compounds is easy, somewhat, because we see the charges. We can say, okay, yeah, chlorine is starting at neutral, it's becoming -1, and bromine is starting at -1, becoming 0. Um, Fairly easy to see where the electrons are going there. However, molecular compounds, they go through redox as well. And so we're going to introduce now a system of kind of accounting for electrons, which is going to be an exciting thing. So we have electron accounting. That is going to be our kind of next step, which we're going to learn what are called oxidation numbers. Which you might also understand is the same word, but you might see this. You might see it written as oxidation states. It means the same thing as oxidation numbers. And fortunately for us, we actually know pretty much all of the rules already for this. They're just kind of all over the place in our chemistry journey so far, but we're now going to kind of aggregate them together into a set of rules for you to follow, or rather just to make things easy for us. Our first rule is any element by itself, the oxidation number is 0. So, if I were to ask you what's the oxidation state of hydrogen in H2, we would say it's 0. Or, hold on. Stop it. Shh. I know, big scary sounds. What's gaining? Relax. Okay. So any element by itself will have an oxidation number of 0. So we saw that before. We had our Cl2 was another example. The oxidation state is 0. Typically, we just write these below the element or above the element. We're going to see that we're going to be able to track these through chemical reactions. You could also have, crazy ones like, sulfur sometimes comes in groups of 8, forms little sulfur molecules. Those are all going to be 0 also because it's the same one. They're all the same element, so it will have an oxidation number of 0. So next rule, again, when you already know, for simple ions, that means it's monoatomic. The oxidation number is equal to the charge. So here's a bunch of random simple ions. Simple ions mean it's one element only, not polyatomic. The oxidation number is just equal to the charge. So nothing too crazy there. The third one is where things get fun. The sum of all oxidation numbers in a compound will equal 0. We can take a look at that. Here is one of our favorite compounds. This one happens to be made of simple ions, so it should be easy for us. If we look, we know that the oxidation number of sodium and the oxidation number of chlorine must equal 0 because it's a compound, right? Sodium in this compound is going to have a charge, of +1, right? And chlorine is going to have a charge of -1. So we should see that 1 minus 1 equals 0. Hooray! This is essentially charge balancing for ionic compounds. So again, it's something that we've already done. So if you can charge balance something, you can kind of figure out the oxidation states as well. So we did the same thing for something like this one, where manganese, maybe we're not quite sure what its charge is going to be. Maybe we have no idea, but we know that bromine must be -1, right, in an ionic compound because that is the preferred charge of bromine. So we know that manganese, I'm just going to make the zeros a little bit more distinct because we're going to use oxygen a lot when we're talking about these, and I don't want to get us confused with O versus 0. Okay, so even if we don't know the charge of manganese, we can figure it out. So manganese -2 equals 0, so therefore manganese must be +2. So this rule is, again, it's very similar to charge balancing. Alrighty, and in fact the same thing is true that if we're looking at a polyatomic ion, the sum of all the oxidation numbers in a polyatomic ion will equal the charge of that ion. And we're going to do that one in just a second. Those are our examples for that one. We'll take a look at that kind of second part of number 3 in just a little bit. But because we're going to need the fourth one, basically, that's why. Alrighty. If all else fails, we kind of do this in order. So we say fluorine gets an oxidation number of -1. Hydrogen gets an oxidation number of +1. And oxygen gets a oxidation number of -2. In this order. And then we continue by electronegativity. Again, we'll see what the heck all this means. We want to give more we would give them their preferred charge as an oxidation state. So, I mean, we could list all of the elements possible here. Anyways, let's go ahead and look at another example, and we'll see how these rules are going to come into play here. So, one thing important to note, that these rules are hierarchical, which means that your higher up rules must not be broken. If you have to break one of these rules, you want to break one of the lower ones. So we're going to see number 1 will never be broken. Number 2 will never be broken. Number 3 probably won't be broken. But number 4 might be broken. So let's take a look at what this means. Let's see what all the oxidation states are going to be in this particular polyatomic ion. So let's go ahead and just go through our rules. First rule says any element by itself. Of course, here we do not have any element by itself, so next. Second rule is simple ions. In sulfate, we do not have any simple ions. That is a polyatomic ion, so not applicable. Rule 3 is going to tell us that the sum of all the oxidation numbers in our polyatomic ion equals its charge. So we should go ahead and just kind of note that. So we know that sulfur plus 4 oxygens will equal -2. That's what our kind of third rule is telling us there. All right, and so we've gone through our third rule. Now let's look at the fourth one. It's telling us fluorine is going to be -1. We do not have any fluorines. Hydrogen is +1. We don't have any hydrogens. Oxygen is -2. All right, that's great. And we would continue if we had more elements by their electronegativity. So you might be tempted to say, I'm going to do it in angry red. Well, sulfur, likes a charge of -2, right? If we do this, we have something that has violated mathematics. So this tells us that we can't just give all of the elements their preferred charges. We're going to have to go in this electronegativity order. So if we look here, we do have a number for oxygen, and oxygen is, of course, more electronegative than sulfur is, right? So let's step back a second here. Let's just go ahead and see what it would be. We can just solve for sulfur, right? We have now an equation with one variable. That's it. So we can just solve for it. If we do, we get sulfur to be +6. So we would write these as saying oxygen is -2, sulfur is +6. What's important to note here that oxidation numbers are only equal to charges in simple ions. This is not telling us that sulfur has an actual charge of +6. Oxidation numbers are not the same thing as charge for anything except simple ions. So this is not saying sulfur is charged. Not the case. But it has an oxidation number of +6. And we're going to see why that's important in a little bit. Let's go ahead and look at a couple more examples. How about we do this one? Let's figure out what the oxidation numbers are for all of the elements in this compound. So this is a compound, right? So we should know that all of these added up should be 0. This is a compound. Okay, so let's go ahead and look at our rules. Do we have any element by themselves? No, of course, we have 3 elements in this compound, so nothing is by itself. How about simple ions? Do we have any simple ions here? Yeah, potassium is a simple ion, right? We know that this thing is really right here. We have our simple ion. Chromate, of course, is not a simple ion, so we can't apply our second rule to it. So this is telling us that potassium should be +1. I'm going to write them on top this time. Alrighty. So we have one of them now, but we still have two that we don't know. So we're going to now go to our fourth rule. We don't have fluorine in here. We don't have hydrogen in here. Our next one says oxygen is going to be -2. And once we have that, we can figure out what the last one is going to be. So let's go ahead and plug in these numbers. We do that. 2 plus chromine minus 8 chromium, I'm sorry. So in this case, chromium is also going to be +6 for its oxidation state. So we would write it right here, +6. There we go. We have figured out the oxidation numbers of all the elements in this compound. Let's take a look at another one. How about we do methane? We're just looking at oxidation numbers right now. We're going to put these in the context of reactions in a bit, Kenji. So reactions can be redox. These are just, we're looking at one compound at a time. So we're just looking at the numbers. We're going to see how to use the numbers in just a second. We're just going to look at CH4 right now. We'll do a reaction shortly. And then we'll talk about the redox, or if something is going to be redox or not. Okay, so absolutely, very nice, Sherry. So we know that C plus 4H must be 0. Neither of these are simple ions, nothing's by itself. We see we have a rule for hydrogen, which is that hydrogen is +1. And so Sherry has seen that carbon will be -4. All right, so we would write that like so. How about this one? Not sure why I wrote it that way. We would do the same process. We'd say, okay, now we have a rule for oxygen. And so we would get +4 for this one. Remember, these are not charges. We don't have C4 plus and O2 minus here. These are covalent compounds. They're shared. It's not ionic. But we're going to see what these are going to mean for us in just a little bit. Let's just do one more by itself. One more compound, that is. And then we'll go ahead and look at some reactions. We'll do two compounds, actually, because I want to show you something. Alrighty, 2H plus oxygen equals 0. We go to our rules. We have a rule for hydrogen that is before oxygen. So we are going to not know what oxygen is right away. If we do the math, we get oxygen is -2. No surprise there. Oh, but here's time for a surprise. If we look at this compound, we can do the same thing. We know that because it's a compound, everything must equal 0. Technically, hydrogen here is a simple ion. Or we could use the first part of rule 4. Again, either way you'll get it right, but technically it's a simple ion here. So we know that hydrogen is +1. Excuse me. If we do this, we get oxygen to be -1. So we get not a charge, just something for us to keep count of our electrons. Alrighty, let's finally see what the heck the point of all this stuff is. Let's take a look at one of Kenji's favorite reactions. And let's see here what is being oxidized, what is being reduced. So thankfully, we have already done all of the oxidation numbers for 3 of these compounds. We saw that we had these for methane. We had those for CO2, and then for water, we had those 2. What is the oxidation number of oxygen going to be in oxygen gas? What's the one that's missing here? What is oxygen's oxidation number going to be on the left? Is that quite right, Sherry? Let's just double check. Uh-oh. We have summoned the angry red face. This one has to be 0, right? It's by itself. Anything by itself, rule number 1. Anything by itself, 0. You could just do this algebra. 2 times oxygen equals 0. Oxygen therefore must be 0. You could do it that way as well. So, I tricked you. Okay, so I know it's easy to kind of forget the first rule, but anything by itself will always be 0. Yep, I totally get it. Lots of rules, things happening. Yeah, I totally get it. Okay, I'm going to erase this angry math here. Let's take a look at this reaction now. Let's look at all of our elements, and let's see what's happening with the oxidation numbers. We have carbon is going from -4 to +4. Hydrogen is going +1 to +1. And we have oxygen that is going from 0 to -2. And technically, we have another oxygen that is also going to -2, but it's the same. Totally lots of rules. So, but now we can apply our idea of oxidation numbers to see what's happening to the electrons in this reaction. So, what is happening with carbon? Looks like it's changing. We're going from -4 to +4. What does that mean about carbon's electrons? We are having oxidation happening here, right? We have a losing of electrons, a loss of electrons. Hydrogen is staying exactly the same, so nothing is happening with hydrogen. However, we see oxygen is going from 0 to -2, so that is going to be the opposite one. That's going to be our reduction. Gang. No. Gaining. There we go. Gaining is reduction. Rig. Yep. So remember, we have our oil here, and we have our rig here. Reduction is gaining. Hooray! Look at all that work we did just for this one problem. And now it's time for me to throw a complete wrench into your... you guys are already confused. Let me just make it worse for you guys. It turns out that carbon is the one responsible for reducing oxygen. So oxygen is being reduced, right? It is gaining electrons. What this, of course, means is C gives electrons to oxygen. And we see that oxygen is oxidizing carbon. That means that O is taking electrons from carbon. This is where the fun begins. We would say, therefore, that oxygen is the oxidizing agent. It is the one doing the oxidizing. And in the process of oxidizing something else, it is being reduced. Did that just go straight over your heads? Probably. As oxygen oxidizes carbon, this is what this is saying here. Sherry, you are absolutely 95% right. Oxidation is losing. So yes, oxygen is getting reduced. So you have the right idea, Sherry. Um, we would be able to say carbon is the reducing agent. However, we have a convention that we actually report the compound that carbon is a part of in the chemical reaction, in the reactant side. So this is the compound containing carbon in the reactant side. So yes, the element, you're absolutely right, Sherry. Carbon is the one who's doing the reduction, but convention is we say the compound that carbon is part of in the reactant. Isn't this exciting? Let's go way back to our favorite equation of all time. We already saw we already calculated the oxidation numbers for this, whether we knew it or not. And so, if we go ahead and look, we remember that chlorine was reduced and Br minus was oxidized. So that means for us Cl2 is the oxidizing agent. I forgot we're going to have to put our sodiums back in here. One sec. So the agent is just the opposite of what's happening. So bromide rather, was oxidized, which means it is going to be reducing something else. And we always refer to the compound doing the reducing as the agent. And here we have chlorine is the oxidizing agent. That's its compound already, so we don't have to change anything. So whatever one is reduced is the oxidizing agent. Whichever one is oxidized is the reducing agent. Isn't that just fun? Yeah, so chemists, we love to talk about things, what's doing what here. Notice also something very exciting for us. We don't need to balance anything, our reaction, if we're doing the oxidation numbers. Let me just put that when figuring out. We do not need to balance our equations, thankfully. So we can have all sorts of crazy reactions happening, but we don't need to actually balance them to do the redox stuff. So, I mean, putting a coefficient of 2 in front of NaBr does not change the compound NaBr. It just means we need more of them to balance out the chlorine, but that's not important for us. Isn't this fun? Hooray. I'm giving you a gift. You don't have to balance stuff. Unless you'd like to keep balancing your combustion reactions. Do we have time for another one? Why don't we just do a couple more of just figuring out the oxidation numbers of a compound. Let's just do a couple more of those to end. I do have homework up on the redox stuff, so you can work through those, as well as on double displacement reactions. Oh, I guess I can have some more fun facts for you. We're going to see that double displacement reactions are always non-redox, which means that everything stays the same in a double displacement reaction. So you can save yourself some time there. You don't have to worry. If we take it, I'll prove it to you, I guess. If we were to look at the oxidation numbers of all these guys, since we're out of time, I'll just write them all. If we were to look at these, we have sodium going from +1 to +1, oxygen -2 to -2, hydrogen +1, chlorine -1 to -1. You will never see double displacement. Double displacements are always going to be non-redox. And so, I mean, technically, yeah, you can go ahead and try them out if you like. You're going to see there will be no change over the course of the reaction. If anything changes, it's redox. So if nothing changes, it's non-redox. And so we're also going to see that single replacement reactions are always redox. You want this particular problem? Have fun with that. We've seen a lot of them, but I mean, we just saw the copper plus silver nitrate turns into silver plus copper 2 nitrate. We had seen that, we had already seen the oxidation numbers for this, but let's write them out anyway. +2 + 5 - 2. Okay. That one is balanced. It's true. This one isn't, though. If we do this, we see that copper goes from 0 to +2. Silver goes from +1 to 0. Nitrogen goes from +5 to +5. Oxygen goes from -2 to -2. We have here redox. Wouldn't that be nice, Kenji? I mean, with the amount of stuff you've learned, I could ask you so many things. I can give you 2 reactants, and you can figure out the products, their states of matter, balance it, figure out if it's redox or not, figure out what type of reaction it's going to be. Look at all the crap we can do now with reactions. Isn't that exciting? Okay, so these are just examples. So you're going to always see that all of the single replacement reactions will always be redox. So that's that. We're going to see that all of our other types of reactions are synthesis and decomp. They could go either way. So you're going to have to actually check the oxidation numbers to see if those would be redox or not. But single replacements are always, double displacements are never redox. Alrighty. Hooray, we made it. So you're going to have plenty of practice on homework. I can give you more practice as well, but I think you'll have quite a fun time with the homework as well. So There's two homework assignments up. One is on double displacement reactions. The other one is on redox stuff. Alrighty. So with that, I will see you guys on Monday. Is Monday the holiday or is that some other day? I don't remember. I think Monday we're still here. It's the 11th is the holiday, right? Um, yeah. Okay, well, I'll see you next week then. What do you mean, Kenji? You have plenty of homework as your study guide. And you have previous exams. Alrighty, we'll see you guys tomorrow. Or next week.